I think it's the first time I go to a conference where I know nobody, and I like it. And so I will try to explain what we do. And okay, so first, so this is the title of my presentation, but let's start with what we do in general, so human robotics. So we use robotics to investigate sensory motor control in human. And on the other hand, very pragmatically, we use robotics to help human. So for the first thing, so you have, for example, these people with 6 fingers. So we try to understand from that the limit of human intelligence. And as you have seen, this guy with a wheelchair, so this guy has cerebral palsy, hands widely oscillating and cannot use a normal wheelchair. And then we had to work on the interface, so human-machine interface, so to make that the guy can move safely and as much as he wants. And yeah, so this is a bit parkour. So I grew up in Switzerland. I did studies there. After I was for the postdoc in Canada, in Japan, and also in USA for 2 years. And after I was assistant professor in Singapore. And after I joined Imperial College, so a long time ago now. And these are some people along the way with whom we collaborate. And some of them I will present our result today. So augmentation, so this is what science fiction has in mind, right? I mean, and actually it's interesting that people had this imagination first in comics and as we will see also second in art, before science. And okay, so one thing is, okay, so if you have this science fiction, then you want to try to make it so in Lego or in real robot. And actually, it's not totally useless in the sense that, especially for surgery, it is a problem that the surgeon has to work together with an assistant. And actually, if you follow what they say, there are quite a few misunderstandings. So if I would be able to do everything by myself, I can avoid this misunderstanding. And on the other hand, so augmentation, so when we work together with somebody, it's maybe kind of augmentation, right? I can do some things that I cannot do alone. And then we try to understand what is happening when 2 people or several people work together. And for example, there's something interesting in children that they touch each other a lot. And maybe it's to acquire some knowledge.
Already connected?
Thank you, but I prefer this. Yeah, thank you. Yeah. Thank you. Okay, so that's a presentation. Sensory motor augmentation with human and with robots.
De ser comprada, dos garotos já aprendeu a tocar violão e a pequena Maria terá aulas de piano.
So I don't know whether some of you know Portuguese, but in any case, so this is natural augmentation, right? So you have actually 1 in 500. You have 1 in 500 births of babies with more than 5 fingers. So it's not so seldom. Now what is happening, so if it's happening in Germany, for example, then actually 2 times I discussed with an Austrian doctor and another time in Stuttgart. And then, so reconstructive surgeon who deal with, for example, if you cut a finger, they have to stick together, etc. And with these 5 seconds, these people would say me, I'll cut it, without, I didn't ask anything, but they would say, I'll cut it. So what would happen is that if you have a baby with more than 5 fingers, quite probably the good doctor would tell you, I'll cut it. No, I think it's better to avoid that. It will create problem, etc. And probably you would say yes to the good doctor, and you would even forget it. But so this family in Brazil, so what happened is about half of the people in this family have 6 fingers, so 6, 6, and 6, 6 also. And so with Carsten Mehring, we were interested in understanding generally what is natural augmentation and whether these people have really more than we do. And so we organized that 2 of these people could come from Brazil, and we make a big expedition. And I don't want to go to the long story because it's like an iceberg. I mean, the study and the result are a small part of all the logistics that we had to deal with. Now, as you see, so for example, we do this spontaneously, but they also do this. So with these other fingers, they do this spontaneously. And in fact, when I picked them up at the airport, after that we had just lunch. And it was quite interesting because I could observe them without telling them, oh, zoo animal, how are you doing this? And it was interesting that I had the feeling they use the utensil in a different way than we do when changing all the time the posture relatively to the tools, so that quite probably these tools are for us, but not for them, too simple for them. And so we did a study. So first, so you see these 6 fingers. So this is a kind of finger here. And what is interesting is that, okay, so as you know, so the fingers can move like this and like this with mainly muscle here. Now, the thumb has intrinsic muscle in the hand so that it can also move like this, so like this and like that. And this additional thumb can also move laterally and like a finger. And so you see this anatomy. So you see, so these are the muscle for the thumb. So we have 4 of them in the hand. And they have 3 additional muscles for the supernumary thumb. So this is anatomy. Of course, you have the nerves that come to that. And when you look at the brain activity, so using, in this case, fMRI, so this is for 5-finger subjects, so I guess all of us. And this is for this 6-finger subject, and you see that there is a dedicated area for this 6-finger. And when you test the sensory, so the perception ability, so you know, so this is a test you have to tell where is the tip of your finger, and they have similar capability for the 6 fingers than for other fingers. Now, we look at the functionality. So basically, we ask them to explore an object. So what we told them is, oh, you have to recognize that object. We don't care whether they recognize the object, but we want that they haptically explore the object. And then we analyze the functionality, so the dependency of the movement. So if in people with 5 fingers, and in these 2 people with 6 fingers. And you see that basically, so in 5 fingers, and this finger is independent, the thumb is independent, this one is independent for haptic exploration. The 3 of them come more or less together, right? And you have about the same. You have the same for the 6-finger subject. In addition, you have that the 6-finger is also independent. Now, we looked at the complexity of the signal. So basically, what we wanted to see is whether the 6-finger is commanded always with another finger, or whether it's commanded independently. And so when you look at the principal component, you can see that these six-finger people need more component to reproduce their movement, so meaning that they have more witch movement. And if you use some machine learning measure of the degrees of freedom, you see that they have more degrees of freedom than these five-fingers people. So basically, it means that these people are more clever than us from the manipulation point of view, and it's not that we saw that they have some myth elsewhere. So for example, we went to play football, and the guy was winning. And so so they have really augmented abilities. And so we did also a test with, so it's kind of a Guitar Hero game, right? So you have to press, and we ask these people to do either with a six finger, or with five of them and one of the other hand. So what we wanted to see is whether they have similar abilities with these six fingers and if they use two hands. And in fact, you see in the learning, so you see that the young guy is learning faster than his mother, but basically in both cases, the learning is similar whether you use two hands or the six finger of one hand. So meaning that these people are able to do with one hand where we need two hands. So for example, so you have this shoelacing. You can try with one hand. So this guy had no problem to learn that. He had never done it before, but he had no problem to learn it. And meaning also that he has planning capability, right? Because basically with a hand, if you can plan something, you can do it. It's about the same. Okay, so this is for this natural augmentation. Now, what about artificial augmentation? Of course, we would like to have the same. Of course, it's quite difficult, and probably we cannot completely. But in fact, so the first guy who really wanted to make a robot enabling working together with three hands is Stella, who is an artist living in Australia. And it's interesting, so he did it in about 1980, of course, working with Japanese group, because Japanese are most advanced in mechatronics and robotics. And as you see, so he succeeded. That was interesting. Now, of course, you wanted to make it more useful. I mean, writing evolution is not enough. We want, for example, for soul work, where you would be able to hold something and working on it. Or as I told, so for surgery is something that is really promising from a patient point of view and from an economic point of view as well. So the first robotic supernumerary arm were done mainly by the group of Asada at MIT. Now, so you have the impression it's fantastic. It is, it's not bad. But in fact, in this case, the robot is moving independently on the human, right? So we have the impression they work together, but it's not the case. So, so we started at about the same time, so at about 2012. We were more interested in not building some robotic arm, but more understanding whether we can really control more than two actuators. And so, for example, we looked at all possible interfaces, also in a more recent European project with Carsten Mehring. So for example, we looked at, so you can look at neural interfaces. Of course, you cannot start to implant, to put an implant in the brain of people just like that, right? So we would like something non-invasive. So we have tried several possibilities. For example, if you have high-density EMG and some clever signal processing, you can extract the activity of the motor unit, so the neuron in the spine. And so we found some possibility to control, but it's very restricted. Mehring, so Carsten did something with ECOG, which is kind of EEG, but on the surface of the cortex. Then he found that he could make independent control of a cursor on the monitor, independent on his hand movement. And so these are neural interfaces. Now, actually, both this and that, it doesn't look like you can control a robot really in a skillful way. So we need, if we want to test real control, real robot and working with 3 hands, then we have to use more practical interface, typically body interface. So in this case, so if you have a surgeon who is sitting, then typically you can use the feet, right? And that's what we did in many studies. So I will go to that after, but first, an example of a study we did. So the idea is that, so if we want augmentation to be useful, then it should enable users to make tasks that they cannot normally, first point. And second, they should do in a way that they are as good as 2 people doing that task. So that's what we tested with an elastic triangle. And this elastic triangle is interesting because you have to control both the position and the force. And it's a bit similar to surgery, where a surgeon has to span the skin to work on it. And yeah, so you have one subject, and yeah, so you test either alone, so using the 3 actuators, or in dyad configuration where you have a partner using his foot. And this is a training, so 1 hour of training over 3 days, and testing of the performance at the beginning and at the end. And it's over 3 days. And these are some of the results. So you see that the success rate is kind of plateauing here, and also the completion time is decreasing, but kind of plateauing. So after this 1 hour of training, it seemed to be enough for this task. Now, when we look at the performance, so it's interesting. So at day 1, we see that solo it's much less good than 2 people. However, after the 1 hour of training, they are basically similar. So if we look, the completion time the same. So the first day, it takes more time to do it alone, but the third day, it is the same or even a little less time doing things alone than with another partner. Also, you ask these people, so the first day, they find it very difficult to work it solo. The third day, this is no longer the case, and what they prefer, so the first day, they don't like working alone. The third day, it is what they prefer. So from that, it seems that it's not a problem for these people with a little training to use 3 hands. And actually, we did quite a few other studies, and roughly what it appears is that it's not a problem to control 3 actuators, 3 arms. What is a problem if you have more than a task? In a sense, so I cannot play chess against myself. I don't know whether you have tried, but I cannot. I have to take side one at some moment. And that's the point, right? You have to have one task. The task could be actually complex. So think about playing piano with 2 hands. The rhythmical complexity can be very high, but at some moment, quite probably, your brain is able to make it one task. And this would be the case here. Okay, so for experiment, so control with foot interface. So this is a foot interface that we developed with where you have position feedback and also force feedback, meaning that I do not need to check where my foot is to know where it is. And this is important because so surgeons actually have some primitive button for the robots. But when you observe surgeons, they are looking where their foot is. So it is important to have feeling what your foot is so that you don't have to check. And yeah, so we looked also at individual motion patterns, so to make it, so if you take pattern general from the kinematics, it's okay. But if you take machine learning identified personalized pattern, you get a better control. Okay, so application, so you have endoscopy. So typically you need a person here to hold the endoscope by the patient. And what we would like is to bring this control at the foot, right? And so that's what we did. So you have control of this soft endoscope that is an interesting new robot developed by my colleague in Singapore. So basically, so you control the endoscope with the foot and you control the two tools with the hand. So if you think about that, it's like if you had a drone, so you control the flight of the drone with the foot, and you have two robots on the drone, and they can manipulate objects. And so in this case, so it's not, we didn't do much control, but we did some control with subject, and they have no problem to use it, and they prefer using Z3 hands than working with somebody. Okay, now it's totally the beginning of this movement augmentation. So one first question is whether we can really increase the number of degrees of freedom, meaning that if I'm sitting and using my foot, it's not that I'm augmented my degrees of freedom. It's just that I'm transferring the degrees of freedom I have from the foot to control a robot. Okay, so when we tried quite a few different interfaces, non-invasive, we couldn't find that there is degrees of freedom augmentation. The only way that seemed to be possible is from directional implants, but so we have to find ways that are non-invasive, right? So this is a frontier. Another frontier is how to provide sensory feedback, because basically all my skin is used, right? I mean, if I want to provide sensory feedback, then it's not clear how I have to do. So whether I have to combine existing sensory feedback or whether, again, I should be able to go to the brain to add sensory feedback. And the other aspect is a learning. So meaning that assuming I'm able to really learn to control an additional robotic arm very well, so will it create problem in my brain? And it's not impossible because, for example, we know example in history of musicians, so playing the violin or the piano, probably Schumann, for example, and so they got problem in the sense that they overloaded their brain ability so that they finally deteriorated their abilities. Okay, there are also practical problems. So to develop variable body interfaces, to integrate autonomous behavior so that you want to solve the degrees of freedom problem. And of course, we should develop application, especially on surgery. I think this will happen within, I don't know, 5 to 10 years. And for that, we have a multi-limb virtual environment that we have acquired from a grant from the UK PSRC, where you have motion capture, 3D VR, and you can disturb the balance, for example, with this robot or train full body interaction. You have the possibility to add up to 4 supernumerary arms. So this is a more variable interface. So you see that. So this is about, so the whole package is about 20 kilo. So it's not a problem to hold it. And from that, we can develop research. Yeah, so next weekend when I go to the SS, I can repair the work, I can fix something alone, what is an advantage. I don't think surgery will be really like that, but it's an illustration. Some fun. So this is at Yokohama at the leading robotic conference. So we had a workshop with Asada, who is this guy. This is his student. And Asada wanted, so we had another workshop the day before in London, and after the workshop, everybody was very happy with Biru, and Asada saying, oh, okay, so in Yokohama we do an augmentation fashion show. And that's what we did. I mean, it's just for fun. Yeah. And so the people were on their poster and didn't know how to react, whether they have to get concentrated on their poster or look. Okay. Yeah, so this is all for this Dr. Adapus ideas, so on motor augmentation. Also, so of course, motor augmentation, it's not only motor, it's also sensory and many aspects of cognition. Now, let's look on haptic communication. So the question is this. So if you have two people moving this piano, so you have done such things, so moving a table or anything together, then normally you don't need to speak that much, right? So you may say, okay, so we take this door or that door, but other than that, you will understand each other what to do. And the same for some people in dancing. And okay, so we wanted to understand how it is happening. And think about that you have to do this with a humanoid robot, and it's kind of horrible thinking because, okay, so you have to tell the robot what? So you have to tell, oh, move 5 cm to the right. What is 5 cm? What is right? And you don't want to be able to have to do that every millisecond, right? Okay, so there must be something else. So to look at this something else, we use a setup like that. So what is happening if you have this guy with a robot, this other guy with another robot, and looking at the individual screen? And of course, the advantage of a robot is that you can connect them as you want. So for example, you can make that I'm connected with you, but you are not connected with me, or we are both connected or not connected. And what we did, basically, so we use a spring force between the two people. And so this is, so you see this. So you have a spring between the hands. And the spring is a weak spring, so it's not that the other can really guide me, but I feel the force from the interaction. I feel the movement of the other. And so we did that, so you see they have to follow this cursor. So both of them have to follow the same cursor, they don't know it, and see their own hand, but not the hand of the partner. And we, okay, so we have connected, not connected, connected, not connected, 60 trial. After that, we ask them, what was the force? They have no idea. On 80 subjects, only 2 of them understood that they were connected. Second question is, does it help or does it disturb? It's disturbing all of them. That's what they think. However, it is helping all of them. So that's what we see here. So you have the improvement of tracking. So you calculate the tracking when you are connected minus disconnected. And then you put as a function of individual performance. And what you see is this. So if the partner is better, then I win with a better partner. What is logical, right? Now, if the partner is worse, I also win. And this is, of course, surprising. And in fact, it's even more surprising that the robots people use for training, for example, in rehabilitation or other physical activity, with a good robot, so with good sensors, you win, but with a bad robot, you lose. So this is kind of a zero-sum game, and this is what people do when they are connected, which is really different. So we wanted to understand what makes a difference, so that's what Atsushi did during the PhD. So these are the data, and first we tested, but finally, is a mechanical connection enough to do that? And so we simulated. So you simulate two agents with linear system, you put a spring together, and you simulate. And what you see is that it's somehow working, but not really, because it's deteriorating when the partner is worse, right? And then, so we tried quite a few mechanisms, so knowing that, so now that we know that mechanics is not enough, so there must be some cognitive mechanism. So then, as cognitive mechanics, we tried quite a few things, but one crazy idea is like that. So if we work together, then your brain, so you do not understand, I do not understand, but your brain understands that what you feel in the hand is related to your visual task, and then your brain is inferring the motion plan of the partner. Right? From the interaction force, your brain is inferring the motion plan of the partner, and in a way, it's like if I had my eyes and the eyes of the partner. And then, because I have two pairs of eyes, so two cameras, I could be more accurate. So that was the hypothesis. We simulated that, and we see that simulation is quite okay with the data. Now, simulation, as you know, you always find what you want, right? So it's not enough. So what we did is that we put this computational mechanism in the robot. So now instead of interacting with your colleague, you interact with a robotic partner, and this robotic partner is implementing this interactive strategy, so inferring your motion plan and combining with its sensor information to move. And when we do that, we see that we see that a human partner, so performance with human partner and with robot partner are similar. So meaning that the mechanism we identified is more or less correct. So catching the essential of the interaction. So we look a bit further into this mechanism. So we did a test where, so some people use trajectory guidance, what is the usual way robots are programmed, for example, in training robots, or they're interacting with a human, or they interacted with this robot partner. And we look at performance, and we look also at the response to questionnaire. And what we found is that, so people found this one, so this one is robotic. They found it's robotic. On the other hand, they found that both human and robot partner are like a human. So they say, I'm interacting with a human. So it's kind of haptic Turing test, right? I mean, the people are not able to recognize the robot. But what is interesting, so they are not able to recognize a robot, and they find the trajectory guidance is a robot. Now, if you ask them what they prefer the robot. And the reason why, so when you look at other answers to the questionnaire, so you see that that they like the robot is probably connected to the fact that the robot is more predictable. It's more simple to understand what is happening. Okay, so they prefer the robot. Now, it doesn't mean that trajectory guidance is definitely good, especially for training. So we did a learning study. So you train on the first day, then you test on the first day, 1 day later, and 1 week later. And so when we did that, and you have again different populations, so some have trajectory guidance, others have a human partner, and others have the robot partner, and finally some have no interaction at all, and they train at the same time. And this is what you see. So you compare 1 week later with the first day. Okay, so this is the solo performance, so when they have no interaction. What you see is that trajectory guidance is much worse. So basically, trajectory guidance is not appropriate at all for learning, and that's something important because, again, that's what people use with robots so far. So you should not use this trajectory guidance. You should use a modality that is more human-like. And in fact, so interaction with a human or with a robotic partner is improving a bit relatively to the solo training. And when you test that on another trajectory that was not learned, so you see similar thing, just of course they have more error because it's not the trajectory that has been learned. Okay, we looked also more recently, so Kärcher did that at children because we wondered, so is that something that is acquired or is that something that you have from the beginning or when would it appear? So unfortunately, of course, we are not yet looking at babies with 1 month. The first thing we did, so we could reduce to 5 years. Same task. In fact, we had to adapt. So for example, the first thing, you make some Mickey, right? That's the first thing. Second, you make shorter training because, as we know, children could not concentrate more than 15 minutes, and so on and so on. And we do also break with ping pong, snack, etc. So, but still, it was not really working. And then what Kärcher changed is that, so basically you tweak the children, you show them their score, and you tell them, oh, look, this other pair did this. And then it's working. Then they concentrate. And so this is the result. So you see that you have the same nonlinear characteristics than in adults. Now, it is that the older children are generally the better partner. Okay? And what we see also is that basically, so if I'm better, then I tend to lead. So it's not something that is imposed, but it seems that automatically, when you are better, you tend to take the lead. And when you are worse, you tend to relax. And this I will not show here, but this we saw also with muscle activity. So when we measure muscle activity, so you have the co-contractions that make your limb more rigid. And what happens is that automatically, when you are better, you tend to co-contract to lead, and when you are worse, you tend to relax. And so you have automatically that the leader is appearing. It's not something that is decided forever. It depends on basically the sensory performance. Okay, now another thing. So what happens? So people were asking me, okay, so 2 people, it's working that way, but what happens when you have more than 2 people? And I thought it was a stupid question, but actually it was a very good one. And so the question is, of course, that, so that's a question I have to you. Who thinks having more than 2 people, so the more people, is that worse or better? Who think it is worse? Okay? Who think it is better? Okay? So now you see the clever people. Eh? Okay, so we did this experiment. So Atsushi wanted to go to a lab in Tokyo. He's Japanese, but he had never been in Japan. and then this lab had 4 robots, so we decided we do it. And okay, and so this is same result as before with 2 people. It's a bit down because he put a lot of visual noise to make different skill level. Okay, so now with more people, we think it would be like that. What happens, the more people, now you see the clever people. Huh? So the more people, the better, okay? And then if you have a bad person in the group, it doesn't matter, okay? Also, another question, so if you have more people, so if you have to learn working with more people, will it take more time or not more time? Who think more time? Okay. Who think not more time? Okay. Okay, so look, so this is at the beginning. At the beginning, it's just from the linear. So this line is from the mechanical interaction, right? And we see that. Yeah, we see that basically in 10 seconds they learned how to interact with the partner, the model of the partner, etc. And when you have 2 or 3 partners, 2 or 3 partners, sorry, so you see that it's the same time basically. So it's not longer to learn with more people. And okay, so yeah, so this haptic communication, so human exchange haptic information during contact. It's not something that you are aware of, but you do it, so you cannot avoid it, right? It's, even if you know that this is, you cannot prevent yourself to do it. And so they identify their partner, and so they adapt muscle contraction to improve haptic perception. Children from 5 years old use haptic communication. And so if you think of communication, right, so we can compare to verbal communication. So verbal communication, for example, as you know, so you have politicians speaking at the same time, but it doesn't seem to work very well in terms of communication. Haptics, it is all the time, and the brain is able to do something with this signal. So it's not to say that haptic is better than language, but it's to characterize the 2 modes of communication. And finally, the more the better. Now, the last thing I want to show is about human-robot augmentation. So basically, because we have seen the way 2 humans interact. So the idea is that we can transfer some of these techniques for communication between humans to let a robot communicate with human. And so you have such robots, so it can be rehabilitation robot to train people after stroke. It can be autonomous cars where you could make communication over the drive wheel, and the car has some sensors, has some actuators, and I have my eyes and my actuators. And so you can conceive the robot as an agent and the human as an agent, and they will decide based on information from the other. And it is important because in the sense of, for example, the car has sensors that you don't have. Or if you think of a surgical robot, the surgical robot will have vision that you don't have. You have another point of view, and so it can complement. So this is important. And so the idea is to make the communication between the robot and the human like it is between humans. And so this could make kind of natural or more natural command for teleoperation, for brain-computer interfaces, shared driving, as I told, and also for robotic superanatomy arm. And so we developed techniques, so Yanan developed this. So using game theory, so basically what is happening is that the human is identifying, sorry, the robot is identifying the human operator, and then using this knowledge to generate motor command considering both my task and the task of the partner, and my dynamics and the dynamics of the partner. And so this is an example, so kind of rehabilitation, so a subject doing that. And you see that, so if, yeah, so now I need it, oh, never mind. So, okay. Okay, so you see that the movement are in all, so you do this and that and this and that. And so the first thing that the subject is playing is no interaction. So when there is no interaction, then the robot understands that there is no interaction, and then generating the motor command considering that. And if you have a weak arm, so basically the subject is taking the arm but not putting any force, then the robot understands that and it augments the motor activity. And then finally, so if the subject, the human, is able to do the movement, then the robot again understands that and adapt and come even to competition where it is breaking the movement to make the task more complicated, so more challenging for the human. So this is this. Now, we looked also whether, I'm soon finished, don't worry. You look also whether the robot could impose a behavior to the human. So for example, so you want that the robot be an optimal trainer. So you want that the robot would be able to impose, for example, a master-slave or a slave-master, or an education behavior where I would assist only the minimal. And so you do this, so if you consider, so in game theory you consider cost function, so kind of energy function. So this is for the performance, and this is, so the robot is considering its effort also and the human effort. And you can change, so you can change how much the human would do or how much the robot does, and see whether the human is adapting to that. And so if this parameter is 0, then you have competition. If you have 1, then it is master-slave, so the robot is assisting completely. And in between, you can do, for example, for education, right? So where you could start by the robot assisting a lot and then decreasing assistance. And so you can change, you could try to induce the behavior. And so in the group of Bastien-Beres, they did experiment for that, and they see that effectively, so when the robot is imposing a contribution, then the human is following. The human is adapting. So meaning that the robot can impose a relationship. Okay, so in summary, so this is basically what people understand by human-robot interaction nowadays. So you have either, for example, in the case of teleoperation or exoskeleton for soldiers, that is force amplifying. So you have that basically the robot is just doing what the human wants. No autonomy. No consideration of sensors. On the other hand, you have this kind of robot for industry where the robot and the human are totally independent. The robot is doing this movement, the human that movement. You may have the impression they work together, but they don't. So this is coactivity where they do not care about the partner. And what we want to try to do is an interaction between two agents, and that can be used, for example, to train in neurorehabilitation, for shared driving, the collaboration, competition. Nobody knows at this point how it should be used. And in all cases, you have to make that the robot can understand what the human wants to do and is able to do, and then adapts its behavior. And of course, you can also use the same for Dr. Octopus, where you have many, many arms. So that's also what we are doing. And voila, that's the end of my presentation, finally. Yeah.
He's shown you a lot of actionable sensory augmentation already. So he's shown you where we put the action in augmentation. And what we do is almost similar, but a little bit from a different angle. So what we do is sensory augmentation, and we do it in science and application. I want to give you a short, very, very short insight into what we perceive as sensory augmentation. And then I want to present mainly two projects that we're doing at the moment. One is feelSpace, which is a tactile compass belt, which we use for sensory augmentation, but which is also by now an orientation and navigation device for the blind. And then I want to show you Hans, which is the newest project that we're leading. It combines our sensory augmentation approach with artificial intelligence, and it's a system that should help blind people to grasp directly where they want to grasp. Okay, so what is sensory augmentation as we define it, or as we do it? And what does it have to do with babies and submarines? So you already heard that you want young subjects, so participants for your studies, because you can study effects that in grown-ups you can see, but maybe they may still be developing in younger people. And in our approach to sensory augmentation, we have the basis, the theory of sensory motor contingencies. So the brain is a big machine that just connects contingencies and connects things and understands the environment, and it also connects actions to perceptions and perceptions to actions, as we have seen. The sensory organs, our sensory organs, the eyes and our ears and the skin and everything is innate, but how to use them is not. So if you watch a baby explore the world, you will see that they repetitively perform actions to better understand their bodies, their muscles, and their organs. So they first have to learn how to use these bodies. They have to use their muscles and also their sensory organs to fine-tune them and adapt them to their environment. What's important that we can do this learning is that there are statistical regularities in the environment. So the same sound wave will always produce the same tone, and the same light wave will always produce the same color. And it's so you quickly learn if you move towards a sound, it will be louder, and if you move away, it will be less loud. You will realize that if you turn your head, that sounds will change in a very distinct manner, and this is something that your brain saves and learns from an early age on. There's this story with a submarine. There's actually many versions of the stories. The one that I know is that you should imagine that you are the captain of a submarine. You've sunken to the ground of the ocean, everything's dark, and suddenly you're attacked by a tentacle monster. And this tentacle monster comes to your submarine, and it exchanges all the cables and buttons, and everything suddenly doesn't work as it worked before. So you're sitting there in the submarine, and you have buttons, and you have levers, and you have maybe a steering wheel, but nothing is working anymore. So what will you do? You're on the ground of the ocean, you have to get up at some point because you don't have food, you don't have air, so it's not really nice to live down there. You will push each button and you will pull each lever and you will just try out what are they doing. What are they doing to the submarine? Am I accelerating? Am I going up? Am I going down, if it's even possible? Yeah, am I steering? Do I go to the right? Do I go to the left? And you will push each button and you pull each lever until you really understand how they play together. And then you will be able to steer the submarine. And that's kind of how we imagine in the beginning of life, every living creature is learning to inhabit their body. There's some from experiment, we know that there's some experimental evidence of this. For example, this very well-known study with two cats, where one cat is strapped into, or two cats are strapped into an apparatus, and one cat is allowed to explore the environment. They actively explore it, they try out their body, and they realize how their motor action is tied to the change in the visual scene. And the other kitten is moved passively. They have exactly the same visual input, but the one kitten that's allowed to explore actively will develop some kind of a normal vision, while the kitten that's moved passively will have problems with vision. There are certain things it can't perceive correctly. And there's a period in life in the beginning, if you don't learn to see and work your body correctly, then it's usually over. For these kittens, yeah, despicably for these kittens as well. So, because I'm not a big fan of strapping kitten into boxes, I wanted to show you another kitten, which is my kitten. So this is Kuro, and he's currently also testing all kinds of contingencies. So I guess the sensory motor contingencies he's already handling very, very well. He has a very perfect paw-eye coordination, and he's demonstrating it here. You can see his eyes, and he's focused, and he knows exactly what he wants to do. He's testing another kind of contingency in his environment, because he knows that if he's going to touch Hermine, she will reliably react like this. Yeah, and this is kind of how babies are exploring the world. They try out their bodies, and they try out everything around them to realize how it works and yeah, what is going to happen in a reliable manner. The question that we asked us at the University of Osnabrück in 2005 was, is it possible that human beings, if they learn in the beginning of life, they learn all their senses and they learn to inhabit their bodies, is it possible that they actually learn a new sense? So can you and I, as a grown-up person, still learn something if we get some kind, so if we have an artificial sensory organ and if we get reliable information, can we learn a new sense? Yeah, and we started researching this in 2005. We know from experiments with sensory substitution that something like this is possible. So we know that if you give visual input through a tactile sense, it's possible to grasp visual information that you will usually only grasp in a visual way. You can grasp through tactile information. So we know this from sensory substitution. But what if we supply information that's not really innate? So what if we add some kind of an organ that's something entirely new? Yeah? And of course, it has to give you relevant information, because the brain is also really good at filtering out things that are not relevant. We all know this. Everything that's not relevant, we forget. So we found that, yes, theoretically, we can do this, but we need something that's statistically relevant and it has relevant information. And I will show you two experiments now where we did exactly this. So one is the tactile orientation belt from feelSpace, and one is the tactile project that I told you before with grasping to the right direction. Okay, so how did our experiments with compass belt look like? We had the compass belts. You can see that there are different models over the time. So we started with something that was quite, yeah, let's say basic. Yeah, this is actually lids from Apple shoes that we use to cover the vibromotors. And these belts have something between 13 and 30 vibromotors. I do think that there was a version with 32, but it doesn't matter. And you wear them around your body, and you can feel the vibration on your hip. Yeah? And they also have a compass, and the compass makes that the northernmost vibrating element will always vibrate. So we have it here, and if north is maybe here, yeah, then it vibrates here on my side. And if I turn, of course, the signal will turn around my body, and it will always indicate where north is. So people get an information about north wherever they go. And these belts were built to vibrate all day long. So our experiments are always long-term studies, because you don't learn these things quickly. I mean, you have to experiment. You have to make the connection between your action, like moving around, and also the sensory experience that you have, like the tactile signals that you receive from the belt. So this is a typical study plan from one of our feelSpace studies, in this case, one of our feelSpace studies with a blind participant. And it entails also a lot of unsupervised training. So our participants were instructed to wear this belt from the morning when they get up until the evening when they go to bed. Of course, not during showering and swimming, they always ask, but other than that, they should just wear it every day. What we also did over these 6 weeks was we asked about their subjective feeling about it, because besides wanting to know whether there was some objectively trackable change. We also wanted to know if people felt a difference in the way that they perceive the world, if they have some sort of a qualitative change through this compass augmentation. So we did a lot of interviews, and we also did a lot of, we also did looked at the results in a very systematic manner. And then we also always did behavioral studies, because we wanted to approach it from all angles. And in some studies we also did fMRI and EEG to track how that changed, if we could observe changes in the brain. In this case, with the blind subject, we did not. But I wanted to show you some results. So in the pointing experiment, the blind subject would walk through a certain area, and we would visit certain landmarks. So we would just show him around. It was maybe a 2-kilometer walk, and showed him several landmarks. And from each landmark, we asked him to point back to all the other 5 landmarks. And then we measured performance with a compass. So he's holding a compass here in his hand, and we knew the correct angle, because we had checked it out before. And we would measure the angle in which he was pointing. And what was quickly shown was that if the belt was turned off, so in the sessions where he was not wearing the belt, we had an environment with the belt, an environment without the belt, and an environment with the belt that was very familiar to him. You can see that the environment where he did not wear a belt was the environment where his performance was the worst. And the familiar environment, especially in combination with the belt, was very, very good. We also did the homing task, which was a dual task at the side. So we asked him to walk the 3 sides or several sides actually, of these shapes. And we started here, walked around the shape. And on this point, we asked him to walk back to the beginning of the shape. And while we were walking on the shape, we asked him to do a mental calculation task. So he was not walking and remembering, okay, now I'm going this step and I'm going this step, but actually he was counting down from 1,000 in 7 steps, so 1,900, 900, yeah, you see, I can't even do it if I'm not in a dual task mode, but he had to do it. And he walked, and after the training, even though it was a dual task, he was able to use the signal, the tactile belt, the compass signal, even subconsciously. So he did not have to pay attention to it. He did it quite well, even though he was counting at the same time, loudly, of course. What struck us as the most interesting thing, so I mean, these are scientific experiments, and we wanted to prove our point that it was possible to make these sensory motor contingencies even in grown-up state. But what struck us as the most important change, was the high emotional impact. Wearing such a belt has a real impact on people's qualitative perception and experience. Because the concurrent, so you always have this vibrating feeling, it gives you a very, very high feeling of safety. That's something that every person who has worn the belt for a couple of weeks says. I feel so safe, I feel like I can never get lost again. Besides that, some people say, okay, when I wear the belt, I understand better how the streets are positioned in relation to each other. So I understand better the street layout and how I'm connected with it. Some said, when I walk a long, straight street that I thought I knew very well, I realized it was curved. I had the same experience when I was wearing the belt. I was walking through a street, I always thought it's straight through Osnabrück, and I realized it's a 90-degree curve. You don't realize this in every day because you don't really pay attention to these things. And what was really fascinating for all the belt subjects was how quickly your brain adapts. So after you wear the belt, you wear it for 1 day, you have phantom vibrations at night. So you will wake up at night and you will feel like you're still wearing the belt. You wear it for 2 days, and you're starting to get the heck out of it. And you understand it better, and you can predict how it's moving. And you wear it for 3 days, you go somewhere where you have gone before, and you know where the belt is going to vibrate. You cannot say afterward whether you wore the belt or not. Your brain predicts every change it's going to make, because it knows your brain has already learned, okay, in this way, the belt is going to be turning like this. So you totally forget whether it was switched on or not. But if something unpredictable happens, if something happens that your brain did not anticipate, like me walking that straight road and then suddenly I have this 90-degree change, then the brain goes, that's not what I would predict. No, that's not. That has to be wrong. So you can see how quickly we make these connections in the brain, and the brain just wants to predict what is going to happen. Okay, so after we did this experiment with blind people, we were asked, can I keep this device? Because it's so helpful. The blind person told us, I can mow my lawn in straight lines. I can suddenly walk straight. I know in the winter when I can't use the white cane due to snow, I know where to turn. I understand the layout of the environment, but I need the belt. I need the constant vibration. I need the compass. So we said, I don't know, it's an experimental device. In the end, we were able to keep it there. Probably you couldn't do it today because of more restrictions in things like that. But it made us research. Okay, how many people do have these problems? How many people could profit from something like this? And we realized, okay, the user group could be blind people. There is at least 70,000 blind people in Germany. That sounds little, but there may be much more, we don't know. Yeah, and we know that there is much, much more people who have some kind of a visual problem. But people who are really blind are usually, it's a very small group, and they're usually in old age because blindness is associated with old age. Yeah, there's a clear correlation between your age and sensory organs not working as they should. But for those who are young and blind, they have a really, really high risk of unemployment. They have so many problems because it's so difficult to get somebody there to a working place and to get them back. It's changing in recent years because there's home office and people can work from home. So we see a lot more blind people integrated into working space. But a few years ago, this used to be a really, really big problem. And we realized, okay, as a primary aid, they use the white cane to get around, and they have some digital devices that they also use. And it made us think, okay, what? No. Okay, I can't call back. But it made us think about... Yes, okay. So it made us think about what problems do blind people really face in navigation. And we realized, okay, orientation in known and unknown environment is difficult. You saw in the pointing task that if they're oriented in an environment, their orientation is really amazingly good. So for all of us who have good visual acuity, we cannot even imagine how many things such a brain of a blind person is processing at a time to get along from A to B. But we realized, okay, real orientation, knowing where am I, how am I turned, and if I want to cross in a straight line, how do I do this? These are just a few of the problems that we realized people had. And we decided, okay, we can solve them with our navigation belt. And that's why we started the transfer. And we did it somehow like the experimental device. It can connect to a smartphone now so that it can not only give you compass information, but it can also give you route information. And so that the two central aspects that blind people use it for today is, for example, they walk around an obstacle not in zigzag lines, but they can actually, they know, okay, I've done a 90-degree turn, and then I do another 90-degree turn, and I walk straight, and then I feel when the object is over, and then I can do another 90-degree turn, and I can do it correctly. And they can use it for navigating. So for example, if I wanted to navigate back to my car, I would ask the belt to point to the parking spot, and then it would lead me if I have to go straight. It would just vibrate in front of me. And if I have to turn and there's a relevant turn coming up, then it will change to the side of my body until I turn, and then it will just go straight again until I reach my destination. So it was introduced to the market, and we sold it to a number of blind people. But we wanted to know, okay, leading back to the studies where we came from, so is it actually helpful to these people in everyday life? We did another study also over a long time. Unfortunately, it was during COVID-19, so we couldn't do behavioral study in a big aspect. We had to do it with only 5 out of 11 subjects. And this is why the most relevant results of these studies are the ones that we have from the questionnaires and the interviews. And the behavioral methods were not really statistically relevant due to the small number. But we had such interesting emotional effects, again, from this kind of substitution, from this feeling, from the constant vibration around the hip. People said that after only 1 week of using the belt, they felt much safer in situations that usually made them afraid. Yeah, usually they feel a big discomfort if they're on a big junction and they have to cross it, or especially walking in parallel to a train platform, because, I mean, if you're blind, you can't see the track, and every blind person has heard of stories of other blind persons falling onto the track. Even though it's not so common, but still people are quite worried about it. On the same time, the confidence level, so the feeling of, okay, I know where I'm going, I know where I am, rose dramatically. It was all statistically relevant. So we're really happy to see this emotional impact that the navigation device has. And of course, it also has a practical application. Yeah, we see it every day. It's just really hard to press it into a scientific study because you may think, so we tend to think, okay, blind people, they are blind, but they are very, very heterogeneous group. Yeah, people can be blind from birth on, people can be blind from a young age on, or people can be blind in very, very late age. So they are very, very different, and they come with very, very different ideas of how to get along. Okay, in conclusion, in our research, we found that tactile compass belts are really functional orientation devices for blind people. And we took one of these belts from science to application, and then we researched again whether we evaluated scientifically whether it was actually doing what it should and whether the effects that we found in research persisted. And we found that actually, yes, participants do feel less discomfort and more confidence when they go along. And that showed us that the effects of sensory augmentation persist in real-world scenarios. So everything that we research actually makes sense. Okay, coming to our second project that is currently being conducted. In a real-world scenario, if you imagine that you're a blind person and you want to go shopping, you have big problems. Yeah, let's say you want to go to the supermarket and you want to buy a green apple. Yeah, then you have to go, first you have to find the supermarket. You can use our navigation belt and you will get it. But then you are in the supermarket. How do blind people do it? I don't know, and I think they don't. Yeah? How do you identify an apple? How do you find the right shelf? Usually they take somebody with them, and if they don't, the only thing that they used to have was a barcode scanner. Yeah? Then they would have to get each product out from the shelf, scan the barcode, and then get some information about the product. So I imagine that that is quite troublesome. But, I mean, today, with modern object recognition approaches, we can start doing things that 10 years ago we couldn't even think about. Yeah? And so we are thinking about providing a system that will help blind people when they go shopping. And it will help them. It will take them to the supermarket. It will indicate where they walk in. It will help them identify the right shelf. And it will also help them identify the right product. Because, and you know that modern AI can differentiate between an apple and a banana. And it can also differentiate between a green apple and the red apple. And soon we will have even more powerful artificial intelligences and powerful object recognitions, so that many things that are on the edge, like very on the cutting edge at the moment, will be possible in a couple of years. That's what we hope. So our system should work like this. Yeah, you put it on, and it's a smaller belt, a wristband that you wear around your wrist, and then it will show you in a similar manner, like the belt, with tactile signals, how to move your wrist. And it will also give you, of course, once you're in a grasping direction and you're close enough to grasp, it should give you an information about grasping. This is what the system looks like in an experiment. You can see that our participant has a camera on his head to film the visual scene. And there's a computer in the background that does all the calculations. You can see here, it's a first prototype of a tactile wristband. It has 4 vibromotors that can indicate up, down, left, and right. Okay, then, yeah, you can see our participant here trying to grasp the right fruit. And at the moment, we have an experimenter sitting in the back giving the instructions, so this was the first experiment, and we did not have yet the object recognition in combination with everything that was necessary, because it looks like it's quite simple. Yeah, you pick out the object and then you just have to move the hand, but it's not as simple as it looks. So look again, you can see that the wrist, there's no diagonal movement yet, so at the moment we can just move up, down, and left or right, and that's exactly what the participant is doing. First move down and then move to the right. Do you want something?
Maybe check the cable connection on the...
No, it's okay. I think it's fine.
Okay.
Okay. Okay, and this is what the object recognition program is seeing. You can see that it identifies the object, and it identifies the objects more or less correctly. Of course, we choose objects that were quite well identifiable. If we had chosen, let's say, a nectarine and an apple, or a peach and an apple, we may not have had this clear result, so we're starting, right? And it's most importantly to connect it also to movement. But we do have this real world scene.
All right, here's your coffee. Right, what do you think about the flowers?
Okay, so I guess this illustrates pretty well where it is going. You see it's not real time yet, and it's a bit slower, and we all think, okay, come on, cross faster. But we have in some form, we already have some artificial hand-eye coordination here, and we're using the tactile wristband as a transmitter of this information to our participant. And I also want to show you another thing here, which is important and leading back to our sensory augmentation approach in the beginning.
All right, here's your, right, what do you think about the flowers?
So if you see him grasping here, you can see the black box is around the target object, and you can see for the object recognition, for the camera, it's occluded, yeah? But it still has to stay right there because it identified the target object as the cup. So having these things is just like our sensory motor approach from the beginning. Our artificial system has to learn to anticipate the movement of the user, because otherwise, at the moment when we have this kind of occlusion, it's going to jump to the next likely thing, and it will give you the flower pot and say, okay, I lost the likely target. Yeah, this had 98%, but then I jumped to something with 58% likeliness, yeah, and then it will suddenly tell you that the flower pot is the coffee pot, because that's just how algorithms work. So our system has to anticipate the movement of the user to really lead them where they have to be.
All right, here's your coffee.
Okay, and in conclusion, we did find that these tactile cues that we can give with the system, that they are really, that they can, in research, that they can already help with grasping. And we believe that in combination with the AI that is already there and that is to come, this is going to be a really powerful tool. And the context that we see is shopping. We see things like on this coffee table, if you drink coffee with friends, or if you have a dinner with your family, or for example, also for blind people, just grasping a door handle or picking up the keys that have fallen to the floor. Yeah, because these are just things that happen in everyday life, and it's really troublesome to find things that are lost from direct tactile view for the blind people. Okay, with this, I close my presentation a little bit earlier. I want to add some formalities because I have to add them. So I have a conflict of interest statement. I have conflicting interests, as you have all heard. I am the CEO of feelSpace, so all the things that I presented here about feelSpace are things that we develop there, and we develop them and we sell them. So that's a conflict of interest. And I do have quite a long list of resources, just so you know it's there. Thanks for your attention.